Right, okay, so what I'm going to look at is required practical 12 on the A-level AQA practical handbook, and that's measuring radiation intensity. And I'll also talk to you about the physics behind that. So required practical 12 is measuring the intensity of a radioactive source. Now this, like gravitational force and like electric field force, is measured as an inverse squared law, and it follows that method in terms of how we would calculate that. It behaves in the same way as the terminology I was looking for there. So let's say we've got a radioactive source that emits radiation not just in a straight line going straight forward, but straight lines in all directions like this. Okay? If we place a Geiger counter at an arbitrary distance of 1, okay, then we will find it will have an intensity of 1. If we place the Geiger tube at an arbitrary distance of 2, then the intensity will be 1 over 4, it will be a quarter. And it would be for 3, 1 over 9, for 4, 1 over 16, etc. It follows an inverse square law. Okay? So the intensity is equal to a constant divided by the distance squared. Okay? If you are asked to compare intensities at different distances, you can calculate the constant and then recalculate for the different distance, or you can simply put it into this form. So intensity 1 over intensity 2 is equal to, and then you've got brackets, distance 2 divided by distance 1, all square rooted, and you can calculate it that way. This is on the data sheet, this is not, so make sure that you are familiar with both. So, what we need to do is we need to get a Geiger tube, we need to get a radioactive source, and we need to get a ruler. And what we are doing is we are moving the source different distances and measuring the count rate. Okay? And then we're converting that into count rate per second. So in terms of what your table would look like, you would have distance, you would have background count, which would stay the same value for all of them, you would have the time in seconds, you would have the count rate calculated per second, you'd have the count rate take away the background rate, okay, and that's important because the background rate would give you a systematic error if you didn't get rid of that. And then we've got 1 over the square root of the count rate, okay, represented by 1 over a half power at the top. So let's talk about background radiation. Background radiation is in the air, it comes from radon under the ground, it comes from cosmic rays in the sky, okay? It's around us all the time. So, without the radioactive source in the room, you need to spend 5 minutes finding out the background radiation count, and then dividing that by the 300 seconds to figure out count per second. And you need to do that 3 times. You need to take 15 minutes, taking 3 background count readings, and then take an average. Okay? For a minimal distance, so let's say 10 millimeters, then what you would need to do is you would need to have a time of around 5 minutes and calculate the count rate per second. When you get to a further distance, what you would need to do is you would need to run the experiment for a longer time. So you would do 10 minutes. And the reason why is because you would want to reduce the uncertainty in your reading. Now, in terms of the corrected count rate, when you plot this against distance, you will get a straight line that does not go through the origin. Okay? The reason why it doesn't go through the origin is because you've got systematic error in your reading, and that is because the radioactive source is either spread out or does not sit perfectly at the edge of the source. There will be a distance. Let's say it's at the back of the source unit. So this systematic error tells us the distance that it is sat away from the front of the unit. Therefore, we would expect a corrected count rate graph against distance to look like that. And that is required practical 12.